Hey, this is Sierra Norwood for week 6. How nuclear bombs work. This week is a little bit different as far as what we were supposed to do for our interactive concept. We're supposed to explain how nuclear bombs work. So I made a PowerPoint slide to help demonstrate that. However, I realized it's going to be backwards for you looking at it, but still I'll use it since I took all the time to make it. So here we go. So whenever we think of the nuclear bomb, we usually think of the ones that were used during World War II on the two cities in Japan. The bombs can have detrimental effects on life itself. The Strategic Arms Reduction Treaty, the START, was placed in order to try to limit and reduce the number of nuclear arms by all the international nations. It calls for a limit of 1,550 warheads. So far, U.S., Russia, and China have the most will have warheads that could strike anywhere in the U.S. That is known. However, we also don't know what's unknown. North Korea has tested a nuclear weapon in 2009, and it actually resulted in an earthquake with a 1.5 magnitude. So the first thing we have to look at is atoms. In the atoms, we have the proton, electron, and neutron. Protons are positively charged, electrons are negatively charged, and neutrons are neutral. The proton to electron ratio in each element is 1:1. Whenever we change the number of neutrons, that's wrong. The proton to neutron ratio, is 1:1 in each element. And then as we change the number of neutrons, we get an isotope. And whenever we change our number of protons, we get a whole other element. So radioactivity, most atomic nuclei are stable, but some are not. These nuclei give off particles called radiation. Any nucleus that gives off radiation is considered radioactive. And a process of emitting these particles is called radioactive decay. A lot of our elements that are located at the bottom of the table are radioactive, or I think all of them actually are. So types of radioactive decay, we have alpha decay, which is where the nucleus ejects 2 protons and 2 neutrons, which are bound together. Beta decay is where neutrons switch to a proton, an electron, and an antineutrino, and this particle is the beta particle. Spontaneous fission occurs when the nucleus splits into 2 pieces. This is the important part for how our nuclear bombs work. During this occurrence, it ejects neutrons, which can become neutron rays, and it also emits electromagnetic energy called gamma rays. Gamma rays are the only nuclear radiation that comes from energy instead of fast-moving particles. Nuclear fission. Nuclear bombs use forces that hold the nucleus of the atom together with the unstable nuclei. Nuclear fission involves the splitting of a nucleus of an atom into 2 smaller fragments within the neutron. Larger amounts of heat energy and radiation are produced, and uranium-235 is one of the most commonly used atoms for nuclear fission, and this is actually uranium-235. Uranium-235 is one of the few elements that can undergo induced fission, which means we help make it happen. The element can be broken down by shooting neutrons into its nucleus. So they're going to shoot neutrons into the nucleus right here. The nucleus absorbs the neutron, becomes unstable. So then whenever it becomes unstable, it splits off. When it splits into the 2 lighter atoms, it throws off 2 or 3 new neutrons. And so then these neutrons continue to make a chain reaction. Usually more than 1 neutron is ejected from each fission, which causes another fission to occur. And this process occurs very, very rapidly. It actually was talking about it was down to the picoseconds. And to make sure that this process occurs, we want to go ahead and you enrich the uranium. Weapon grade uranium is composed of at least 90% U-235, and so basically this process right here is the whole point of how it occurs. So fission bomb design, we have two different types of nuclear weapons. We have fission bomb designs, which is what was designed or what was dropped on Japan, but we also have fusion bomb designs, to which we'll get to in just a minute. So fission bomb designs, with it, the fuel is kept in subcritical masses, which won't support the fission, which basically means we want to keep it separated so it can't go ahead and detonate beforehand. So critical mass, what we call critical mass, is the minimum mass of fissionable material required to sustain the nuclear fission reaction. And basically this is going to present a couple of challenges to make it work. So the first hurdle that we have to overcome is somehow bring all the smaller subcritical masses together in order to form a supercritical mass, which is more than what is required to cause the reaction. Free neutrons need to be introduced into the supercritical mass in order to start our reaction. So we have a neutron generator as a small pellet of, that's supposed to be polonium and beryllium, which is in the fissionable fuel core. The design needs to allow the most fission to occur before the bomb detonates. And so some of our triggers that we could use, a simple way is to make a gun that fires one mass into another. The explosive fire and send the bullet down the barrel. The barrel hits the spear and generator, which initiates the reaction, and the fission reaction starts, and we get the bomb imploding. So fusion bombs are really more of what's used today. They occur when the nuclei of two atoms combine to form a single heavier atom than the original one. With higher temperatures, nuclei of the hydrogen isotopes deuterium and tritium can fuse, which release large amounts of energy, and weapons that rely on this technology are called fusion bombs. These are actually more effective than the fission bombs, so that's why we've kind of went away from the fission and more toward the fusion. So whenever we look at fusion bombs, they have a higher efficiency and yield a greater energy release than the fission bombs, but we have some problems that we have to overcome, just like with the fission bombs. So the deuterium and tritium are both gases, which can be a little bit harder to store. Tritium is in short supply and it has a short half-life. The fuel has to be replenished continuously, and the gases have to be highly compressed at high temperatures in order to start our reaction. So the solutions use lithium deuterate, which is a solid compound that doesn't decay at normal temperatures. The fission reaction is used to produce tritium from lithium. Fission reaction results in X-ray radiation, which provides high temperature and pressures to initiate fusion. And the bomb fusion has two stages. So the two stages are fission and fusion. So basically, we're doing fission, but we're taking it one step further and proceeding to fusion so that we get a more effective bomb. So the bomb sequence of events. The bomb fission implodes, resulting in X-rays. And X-rays heat the inside of the bomb and the taper. The shield prevents premature detonation of the fuel. The heat causes the taper to expand, exerting pressure inward against the lithium deuterate, and lithium is squeezed, resulting in compression wave that results in fission in the plutonium rod. So here we have our high explosive lenses. Our uranium is in here, this bigger or thin circle. We have a vacuum, and then here we have the tritium gases, and here we have our plutonium and uranium. So here is actual a foam, you know, kind of keeping them separated. Here we have our uranium in this square. We have our lithium here, and then we have our plutonium spark plug, and then we have our casing. So basically, we're wanting this to occur and then go down. Okay, so fission rod gives off radiation, heat, and neutrons. The neutrons go into the lithium to make tritium. Higher temperatures and pressure result in the tritium, deuterium, and deuterium fusion reactions, resulting in more heat, more radiation, and more neutrons. The neutrons from the fusion create fission in the uranium-238 pieces, and fission from taper and shield produces more heat and radiation, and our bomb explodes. So, some of the health risks that can be associated with nuclear bombs, number one, just the damage created from the bomb exploding causes heat, pressure, radiation, and then the radiation fallout. So basically, if you're in the site, like, you know, right on top of where the bomb is exploding, nothing's going to be left anymore, because basically you're disintegrated by the heat and the pressure and everything. Basically you're blown to bits, to be nicely. And so basically it depends on how close you are to the bomb implosion site. This was actually pretty interesting. It said heat at the hypocenter is around 500 million degrees Fahrenheit. So basically, as far as the immediate area, burns, radiation exposure, and the flying debris are going to kill you. If you're out further, you know, you may survive, but ultimately you'll really have a slow death because of the radioactive particles. So the fallout particles enter the air and the water supply in the area, and they're consumed by the people and the wildlife in the area. And so we can get nausea, vomiting, cataracts, hair loss, anemias, cancers, infertility, birth defects, and genetic changes from the radiation. And we can kind of see all of this whenever we look at different areas where there have been nuclear bombs that have been detonated. We see higher, you know, like cancer rates, more birth defects, more genetic changes, things that we can see. And also, like, if we have a nuclear power plant meltdown and everything, like in the Chernobyl area in Russia, the radiation is very high in that area, because there have been some studies done on the wildlife and everything, and there's been birth defects and different changes and everything, even in the wildlife that lives around the area. Obviously nobody lives there anymore, but they still go in periodically and do studies, and you know, they have to wear certain devices that measure the radiation and everything, and they can only be in there so long of a time to limit the radiation effects on the body. But similarly, you know, we can see the effects of radiation whenever we look at things that have happened in the past. And that was my reference. And that was week 6, how nuclear bombs work.